Okay, let's continue. So today as well, not much will be done by way of computational examples. We still have a lot of important ideas to talk about. Ideas are important. So last time we spoke about concavity. Last time. We had the idea of concavity. So we had concave up, like a cup. Concave up, like a cup. Right, so this is if your graph is like this, like that, like that. Right, it can all sorts of behavior, but it is a matter of shape. And the defining characteristic of this was the second derivative of x values here will be positive. Right, so at any point you pick on a region where a graph has this sort of smiley face behavior, it's curving like that, you'll notice that the second derivative is positive. You also had concave down, like a frown. So this is when you're shaped like that, or like that, or like that. Right? The defining characteristic here, where the second derivative is negative. So if you were to pick any random x value on this region where you have sort of this frowny face situation, you'd realize that if you take the derivative and then take it again, you'll get a negative value. So that was concavity. Now the next thing I want to define for you is a thing called inflection. So this an inflection point, let me define inflection point. An inflection point is a point at which we switch concavities. So it would look like you were one concavity and then you hit a point and you do now the other concavity. So this is an inflection point. Or this is an inflection point. This is an inflection point here. This is an inflection point here. So these points here are inflection points. Notice that once I was before this point, I was concave down, and after that point, I am concave up. So there came a point where I switched from one concavity to the other concavity. Such a point is called an inflection point. Right? Now, inflection points and concavities and all this sort of thing, they are important, and it comes down to consider what these would mean given some interpretation. For your function. So, math people go around, we care about functions as an end in themselves. You're so beautiful, I want to know everything about you. Most people don't care about functions, right? You don't care about these equations and solving equations. What you should care about is what the function represents to you. So most people probably don't care about the actual graph, but sometimes if you graph something, it can tell you information about the thing that thing is actually graphing. So what is the kind of thing that concavity and inflections would tell you about a graph? Now, we saw last time that increasing was the notion of the graph moving up as you go from left to right, right? And so these two over here, these are increasing. These two over here, these are considered decreasing. So you're moving down as you go from left to right, right? So increasing or decreasing is the idea of getting bigger or smaller, right? So when your graph exhibits a behavior of going up as you go from left to right, basically the interpretation is whatever that graph is measuring, it's getting bigger, right? So this situation, your interpretation is going to change very drastically depending on what that is, right? So if you are talking about, you're measuring profit, right, from you selling products or providing a service. Good, bad, right? Going up, you want more profit, you want to make more money. Okay, so these are good. You start losing money. These are bad, so the interpretation would change. If, on the other hand, this was, say, gross malignant cancer cells in my lungs. Now this is bad. That's good, right? And, well, if there's a graph at all, it's all bad. But you get what I'm saying. I'd rather be, if I have to be in that situation, I'd rather be in this situation than in this situation, right? Whereas if we're talking about profit, I'd rather be in this situation than that situation. Now, that's in terms of increasing and decreasing. When you start talking about concavity and inflections, you can put a whole other dimension on that. So now, let's go back to the profit idea. Profit is increasing. There are several ways you can be increasing. What would be the distinction between this kind of increase and that kind of increase? Notice what's happening in this situation. Okay, business is good, profit is increasing. There came a point where now, wow, business is great, right? So if you're tracking profits for your business and you see a behavior like this happens on a graph, what does that mean? We were good, but something happened that made things great, right? And if something happened that made things great, you would tend to want to do more of that thing. So you would have to identify, so one way you can go about making things better, making things more efficient, getting more profit, is figure out where all the inflection points are located on the increasing part of the function. And if it was concave down and then concave up, that behavior, whatever was happening at that point in time, we want to do more of that thing, right? In this situation, you're still okay, profits are still increasing, things are great. Now they're just good. I mean, we're not losing money, but at the same, we don't have the same oomph we did before, you know what I mean? So something happened at this point where, yeah, things are still good, but they're not as good, and I can kind of see if this was to continue, right? So this is like, okay, things are good, but I see something coming up on the horizon. Whereas, wow, things could never be better. They're just getting better than they were last time, right? So you can have different dimensions as to increasing, right, or decreasing. So it's not it's going up. No. How is it going up? We want to be able to plan for the future. We want to be able to predict and make our future better than the past was. So one way to identify that, how to do that, is inflection points, right? So it's not just, oh, the second derivative is positive and I need to know this for math class. No, it actually has meaning out there. Once your function is actually tracking something, seeing the concavity and the inflection, it actually tells you another dimension on the story. Not only is it going up, how is it going up? What is this going to mean a few days from now, a few weeks from now? What happened in the past? What happened that caused that change in behavior? We should do more of that, or we should do less of that, right? So there's a whole interpretation that you can throw on top of these things. So knowing when these behaviors will happen is going to be very important. So concave down, if you're concave down and increasing, it means you're increasing, but you're increasing slower and slower and slower. Whereas if you're concave up and increasing, you're increasing but faster and faster and faster. You're increasing by more over time, right? Whereas if you're concave down, so concave down decreasing means you're decreasing faster, more rapidly, right? So if this was profit, wow, we're losing a lot of money and it's getting worse over time. Okay, something happened and we're still losing money, but it's not that bad. So maybe we should do more of whatever that was. Maybe it can turn things around for us, right? So if you're decreasing, concave down means the decrease is happening faster and faster and faster. Whereas concave up means the decrease is happening slower and slower and slower. It's still decreasing overall, but it's happening slower and slower and slower. And so you'd have a lot of arguments for certain things For example, like, one argument that some people always talk about with climate change, for example, is that, well, global temperatures have always been rising. But no, Industrial Revolution, that happens. There is something different in how they're rising, right? And the people who don't realize that is people who don't know about concavity. Like, yeah, it's increasing. I know it's going up, but there's something different about how it's going up. Something is on the horizon. It's not good news, right? That kind of analysis comes from a second derivative kind of analysis, right? Your first derivative is going to tell you, oh yeah, it's going up. When you want to talk about how is it going up? What does this mean? What does the future hold? Now you're talking into second derivative territory, right? So it's not just something you can calculate. It has meaning at the end of the day. So I want you to appreciate that. So a lot of the word problems that you're going to have to do are just things you have to know about in general. Just being able to look at a graph and read it is a very important thing, and it can help you figure things out and know when something is on the horizon, know when, yeah, overall kind of the same thing's going on, but something is different. I can feel it. Like, no, you can't show it, right? This is, yeah, things are still great, but I kind of feel like we're not selling as many products. What are you talking about? We're making a profit. Yeah, but I feel like something's good. Then you're going to find out, oh, at this point, a competitor opened a store around the block. What happened right here? We're not selling as much as we used to, right? Now you know, oh, there's something I have to worry about around the block, So concavity, inflection, very important. They really tell you a lot of information at a different level than just seeing something going up or down will tell you. Okay? So knowing when these things occur and being able to pinpoint a location where concavity changes is an important thing in general. Now, to go for, say, let's talk more about the first and second derivative and what they can tell us. So, two important tests. So, two important tests that we're going to be able to do. So, there's going to be something called the first derivative test. And the second important test I want to talk about is the concavity test. There is such a thing as the second derivative test, and I might mention that in passing at one point, but for us it's not going to be very useful because the second derivative test will actually give you the same information as the first derivative test, and in most contexts we'll be doing this first anyway, so you're not going to need a second derivative test really. But these two, I would say, are really important. You need to know what these guys are about. Now, because this test has concavity in it, of course it involves the second derivative. Okay. So, first derivative test. Now, here's the first derivative test shows you one of the reasons why the first derivative is actually a super important thing to actually calculate. Not only can it tell you about increasing and decreasing, but it can actually tell you about something else. It can tell you to find where f of x is increasing, decreasing, or has maximums, minimums. So now, there's also the idea of having a maximum or a minimum, meaning like a peak, right? The top of a hill, right? Versus a minimum, the depth of a valley, right? Knowing these kinds of behaviors is also kind of important, right? Now, if you're looking at your profit and your graph is like this, that's worse, right? So you were doing well, there came a point where now you're actually doing bad, you're actually losing money. Identifying the point where that occurred might be a very important thing to know. You would be identifying a maximum in this situation. And it turns out that the first derivative can help you identify not only increasing and decreasing, but also maximums and minimums. And how would you identify a max or a min? Well, for a maximum, for that to occur, you'd have to actually be increasing on the left side and decreasing on the right side, right? That's how a maximum happens. You're going up on this side, but then on this side you're going down. It means that in the middle, there was a point where you were as high as you could get. Similarly, minimums. If you were going down on the left and up on the right, you would attain a minimum possibly. The first order is what's going to help us actually identify these scenarios. Now, with certain functions, we can actually identify this easy. For example, with parabolas, you can find maximums and minimums using the vertex formula. Turns out though, for other functions, there is no general formula. So if we want to figure out maximums and minimums in a general sense, the first derivative is actually how we do it. So for one, you are going to find f prime and the critical points. Now, what is a critical point? This is points where f prime equals 0 or f prime is undefined. Right? You need to identify where is my derivative equal to 0 or where is it undefined. Now, I'll talk a little bit more about why these 2 points are important in a bit. So you need to identify the critical points. Find the first derivative and then figure out when is it 0, when is it undefined. These are going to be critical points. So you plot critical points on number line, test the intervals. So let's say at this point you draw a number line, you're going to test it in the first derivative. And so let's say x here, your x, this is a critical point. What you're going to do is you're going to plug in values a little to the left and to the right. I'm going to pick a value over here, call it x0, pick a value over here, call it x1. And what you're going to do is you're going to plug these into the first derivative. You're going to find the first derivative, x0. And you're going to find the first derivative of x1. Right? So you find the derivative in general, figure out where it's 0 and undefined. Then you're going to figure out what the values are on either side of all of these points. And 3. You're going to conclude it's on the following. So here's our critical point. If your f prime is positive over here, but negative over here, it means you are going up and then you are going down. Versus if your f prime is negative over here, but positive over here, it means you are going down, and then you are going up. And thirdly, if f of x is continuous, so if x is continuous, so you're at a critical point and it's actually a point that exists on the function. You go up, you hit this point, then after that point you go down. This means a maximum occurred. Here, again, assuming that your f of x is continuous, this means you're going down, you hit a point on your function, and then after that point you started going up. This means a minimum occurred. Otherwise, no maximum. So if you don't have this behavior, or the function is not continuous at this point, you don't have a max. And if you don't have this behavior, or it's not continuous at that point, you don't have a minimum. But a maximum and a minimum will have this behavior. You'll be able to locate points where your positive, your first derivative is positive on one side and negative on the other side. This means you went up then down. That's a maximum. Versus going down then up. That's a minimum. And this is called the first derivative test. You'll be able to identify where your function is increasing and decreasing. Remember, increasing means derivative is positive. Decreasing means derivative is negative. So you can identify all your points of increasing and decreasing, as well as if any maximums and minimums will occur, all by doing this test using the first derivative. So that's the first test you should know, the first derivative test. It's very important. And we're going to go away from this, but we'll come back to using it in later sections. I just want to, at this point, I just want to tell you about all the reasons why derivatives are important and just some properties about them. Then we'll go learn about some calculations. Then we'll come use these. What I'm telling you now, we'll use in applications down the road. So that's called the first derivative test. Find your derivative and the critical points by setting it equal to 0 or undefined. Find all the x values that causes this to happen. Then you're going to plot them all on number lines, and you're going to plug in numbers in between them in the first derivative. And based on the behavior that results, you'll make certain conclusions. Any questions? And that's the first derivative. Second test is the concavity test. This identifies whether you're concave up, concave down, and inflection points. Hopefully you see at this point why it's important to actually know when these guys occur. So first thing, so now you're going to find F double prime and critical points. So again, critical points are just a fancy word for where is my derivative 0 or undefined. So you're going to use the second derivative now. So you would have found the first derivative, maybe have done the first derivative test. Then you can move on to the concavity test. Find the second derivative. Set that equal to 0 or undefined. And you kind of follow the same procedure, except step 3 is going to be different. So plot these on a number line. Technically, you don't have to plot them on a number line, but I think it's nicer to visualize it and just keep things in check, knowing that you're not missing anything. So we're going to have a number line. And what I like to do to make sure I don't mix them up, I'll actually label the number line double prime, so I just know everything I'm plugging in here, I'm plugging into the double prime. So let's say here you have x, that's a critical point for you here. Pick a random number, it doesn't matter, just as long as it doesn't overlap with some other critical point. And I'm going to compute the second derivative at this point. Pick another random number, I'm going to compute the second derivative at this point. Conclude based on. So you would have several situations here. So here's your x value. Now two things can happen. You can pick a value over here where your second derivative is positive, and then it switches to negative. Positive means concave up, so I usually draw something like that, like a smiley face to remind me, okay, that's concavity. It could be going up, it could be going down. Second derivative doesn't deal with that. Second derivative tells me how am I shaped. I'm shaped like a smiley face. Here, shaped like a frowny face. Versus over here, if I had this guy is negative versus this guy is positive, then here, shaped like a frowny face, here, shaped like a smiley face. And here, if our function, if f of x is continuous here, this signifies a point of inflection. So here, if f of x is continuous here, then this also signifies a point of inflection. So here you're concave up to concave down, so you could be this, you could be increasing, or it could be that. Right? So this situation would signify one of these two behaviors happening, whereas this situation would be, could be this if it's increasing, or it could be that if it's decreasing. So one of those two would happen in that situation. Notice that you have to change signs on either side. So you're positive on one side, negative on the other. Or you're negative on one side, positive on the other. Otherwise, inflection does not happen. Okay. So an inflection occurs where you switch concavity. You switch from a concave up to a concave down, or you switch from a concave down to a concave up. That shows itself in a change in sign when plugging random values. And we'll do some examples later, but I just want you to have that idea. So that's called the concavity test. Now, I want to summarize some important ideas here. Summary of functions. So, when you're talking about this whole calculus game, it's going to be a certain kind of function. It's all about using the functions to glean certain information. So we can talk about a function, and we can talk about what does this function tell us. And then we can talk about how does this function tell us. So if I'm looking at this function, what information can I get from it, and how will I know that that's the information being communicated? So, for example, you can have a zeroth derivative, an original function, f of x. So if I tell you f of x equals blah, what information can you get from f of x? What do you know, what information do you get from the original function? What kind of info?
f of x equals?
Yeah, I tell you y equals f of x. What information could you get from that? What would that tell you? What are the kinds of things you can calculate? Yeah?
If the function is positive or negative.
Yeah, but more specifically, like points on the function. Right? These are points on the function. So positive would just means the point is located above the x-axis. Negative would be it's located below the x-axis. Location, current status, things of that sort. So if the question was, how much profit did we make this week? The original function is what you're going to look at, the original profit function. You look up x value is whatever date for this week, and the output is going to be the profit. What's our current status? What's our current location? What is the current situation at this point in time? The original function will tell you. And how does it actually tell you? Well, easier than you would think. So if y equals f of x, plug in x and compute the y. So if someone wants the current location, the current status, you're going to go to the original function, you're going to plug in the current time or whatever input you need, and then the output, the y, is going to be the answer to that question. Now, of course, if possible, you can find a first derivative. Now, what kind of information does the first derivative give you? Well, it can tell you about increasing, decreasing. It can also tell you about maxes and mins. So if the question is, are profits going up? Are profits going down? Is business good? Is business bad? Right? The first derivative is who you would look at. And have we hit the maximum profit yet? Are we at a minimum profit? Have we passed the dip? Or something like that. Maxes and mins. How does it tell us? Well, the first derivative test is what we do here. You can figure out all of this information using the first derivative test. Then you have the second derivative. What information can this give us? Well, it can give us information on concavity. It can also give us information on inflection points. How does it tell us? Well, the concavity test. So each of these functions have their own uses. And when you're looking for something specific, you should know which function should you be looking at. So let's say you wanted to identify a maximum point on some function. What are you going to do? You're going to use the first derivative test, right? You're going to find all the critical points and you're going to locate. Do I see the behavior of increasing on the left, decreasing on the right? If the answer is yes, now you want to know, okay, at what point did that happen? You're going to go back to the original, because that's how you figure out the points on the function. You're going to plug in that value into the function, and you're going to get the y coordinate. So then you'll be able to say, at this location, there's a maximum. Right? You'll be able to actually say the location. So at any time, if you're looking for a location or current status, use the original. If you want to figure out increasing, decreasing, maxes and mins, you should be looking at the first derivative. You want to figure out concavity and inflection points. How is it increasing? Is life getting better or worse? Is it getting better or worse, faster or slower? Those kinds of questions are answered by the second derivative. So each of these three different functions, they have very different purposes. You need to know what it is that you're after and choose the right function that's going to give you that thing. This gives you location, that gives you increasing, decreasing, maximums and minimums. This gives you concavity and inflections, right? Which is an interpretation on how is it increasing or decreasing. So that's very important to know. So you should have an idea of what each kind of function, what kind of information, why would I care about this function, what is it going to tell me. Now, probably the last thing I want to talk about today is, so if we can find derivatives, these are the information we can get. However, the derivative is a limit. Now, note, the derivative is a limit. So, it turns out it may not exist. So there are times when you want to be able to do this sort of analysis, but you're not in the situation where you can do it, because you can't actually find a derivative. So what I wanted to start with next is, how would you know when a derivative isn't an option to solve this kind of problem? When does a derivative not exist? So let's talk about the existence of the derivative. There are three cases in which a derivative will not exist at point. One, at sharp corners and cusps, you actually can't find a derivative there. So if your function looks like this, or that, or that, right? At these locations here, it turns out that your derivative will not exist. In fact, if you look at y, this is a common example, y equals the absolute value of x, that looks like a v, as you know. It turns out that if y prime does not exist at x equals 0. It turns out you can actually calculate that. That's actually not that bad. If you set f of x equals the absolute value of x, then your f prime is going to be the limit as h approaches 0 of f of x plus h minus f of x over h. So this means if you wanted to find the derivative at 0, that will be the absolute value of 0 plus h minus the absolute value of 0 all over h. We'd end up with the limit as h approaches 0 of the absolute value of h over h, and that does not exist. We actually did this particular example in class with x's, right? Limit as x approaches 0, absolute value of x over x. What happens is, as you're coming from the right, this returns a positive value, you get 1. If you're coming from the left, it returns a negative value. The graph of this looks like that. Right? So at 0, the limit did not exist. But this limit is a derivative. It means a derivative won't exist here. So that's a concrete example, the very typical example that's used here. But it turns out at sharp corners, you will never be able to calculate a derivative. Why? Because there's no real tangent line. Remember, the derivative just finds the slope of the tangent line. Where you zoom in, it starts to look like a line. Sharp corner will never look like a line, no matter how much you zoom in. There are tons of lines that you can draw through this, and none of them would be better than the other at looking like that sharp corner. There will be no defined tangent line. Right? We can draw any tangent line we want, but if I zoom in, it's never going to approximate the function. You can't approximate a sharp corner with a straight line. So that's the first case. So if you're looking at a graph and there are a bunch of sharp corners, your derivative won't exist there. Now, of course, in these cases, you would still consider those critical points. There's still going to be points you want to pay attention to. You just need to know a derivative won't work. So that's the first situation. The second situation, you will not be able to find a derivative. This one is a little bit more obvious, probably, where f of x is not continuous. Again, you can't draw a tangent line to something that's not there. Continuous. Okay. So if you have a hole, or you have like an asymptote or something, so that's at A. Say that's at A. Right? F prime of A does not exist for the above. Right? No matter how much you zoom in, a gap isn't going to look like a line, an asymptote isn't going to look like this gap in the function here isn't going to look like a straight line. You can't actually draw a tangent line to the curve. There's no curve to draw the tangent line to. So wherever your function is not continuous, you can't find a derivative. So sharp corners, bad for the derivative, can't work. Where our function is undefined, bad for the derivative, can't work. Where a third place, at points where a tangent would be vertical. Now, sometimes you have functions that have these weird behaviors. Now, of course, a function has to pass the vertical line test to be a function, but you have a lot of functions that behave in this weird way where they go vertical literally for a split second, like at one point. So it's a very steep descent, like a really steep inflection point, and then it goes off like this, right? And the function behaves in such a way that if you were to zoom in on that point, the best thing to be a tangent line would literally be a vertical line. So this would be the tangent line. Right? The closest line that fits this function is a vertical one. But we already know that vertical lines have no slope. Right? Slope doesn't exist here. So you have functions that have this behavior where for a split second they go vertical, and yeah, at that point where they do that, you can't actually find a derivative. That's really all I wanted to talk about today. So, main takeaway, know what each derivative is, what it can actually tell you. Know when a derivative is not going to work out. So know why is the first derivative useful, why is the second derivative useful? Why was the original function useful in the first place? Know all that stuff. Know the first derivative test, concavity test. We'll actually use all this stuff later.